why empty space is not empty. Point to the space between your hand and the screen right now. What's there? Nothing, right? Just air, or if you're in space, just vacuum, empty, blank. So a whole lot of nothing, stretching in every direction. Here's what 50 years of physics has taught me about that nothing. It's not nothing. It never was nothing. And the more carefully you look at empty space, the more you realize it might be the most violent, the most energetic, the most mysterious thing in the entire universe. And so I'm Leonard Susskind, and I want to tell you something that should fundamentally change how you see the world around you. And it's the space between atoms, the space between stars, the space between you and the wall. It is not empty, it is screaming with activity. And the fact that you can't see it, can't hear it, can't feel it, that's not because nothing is happening. It's because everything is happening so fast, so violently, and at such a small scale that your senses were never designed to detect it. This is not speculation. This is not philosophy. This is experimentally confirmed physics, and it has consequences that reach from the smallest distances we can measure all the way to the fate of the entire universe. Let me start with what seems like a simple question. What is a vacuum in everyday language? A vacuum is what you get when you remove everything, pump out all the air, remove every atom, every photon, every particle. What's left? Nothing. Emptiness, the void. That's what classical physics would tell you. That's what Newton believed. And that's what seemed obviously true for centuries, but quantum mechanics destroyed that picture completely, and it did so in the most spectacular way imaginable. And in quantum mechanics, there's something called the Heisenberg uncertainty principle. You've probably heard of it. And it says you can't simultaneously know a particle's exact position and its exact momentum. The more precisely you know one, the less precisely you know the other. And most people think this is just a limitation on measurement. Like maybe the particle has a definite position and momentum, we just can't figure out both at the same time. No, that's wrong. And the uncertainty principle is not about what we can know, it's about what exists. A particle doesn't have a definite position and momentum simultaneously. Those properties are genuinely undefined. Hence, blurred, spread out across possibilities. Nature itself is uncertain. Now here's where it gets wild. The uncertainty principle doesn't just apply to particles, it applies to fields. And this is where the vacuum becomes something far stranger than empty space. In modern physics, the universe is not made of particles, not fundamentally. The universe is made of fields. And the electron field, the quark field, the electromagnetic field, the Higgs field, these fields permeate all of space. They're everywhere. And right now, as you're listening to this, there are quantum fields occupying every point in the space around you, inside you, through you. Hence, what we call particles, electrons, photons, quarks are actually tiny vibrations in these fields. An electron is not a little ball floating in space. Hence, it's a localized excitation, a ripple, a disturbance in the electron field. A photon is a ripple in the electromagnetic field. Hence, every particle you've ever heard of is just a field vibrating in a particular way. Now here's the key. Because of the uncertainty principle, these fields cannot be perfectly still. Hence, they cannot sit quietly at zero. That would require the field to have both a definite value, 0, and a definite rate of change, also 0, simultaneously. And the uncertainty principle forbids that. And so even in a perfect vacuum, even when you've removed every particle, every bit of radiation, every trace of matter and energy, the fields are still fluctuating, they're still jittering, and still buzzing with activity. This is called the zero-point energy of the vacuum, and it's not a theoretical curiosity, it's the ground state of reality itself. Think about it this way. Imagine a pendulum. In classical physics, you can stop a pendulum completely, it hangs straight down, motionless, zero energy. But in quantum mechanics, you can't do that. And the pendulum always has a tiny bit of motion, a tiny bit of energy, even in its lowest possible state. You cannot extract this energy, you cannot cool below it. It's the absolute floor of the system. And the quantum fields that permeate space are like an infinite collection of pendulums, one at every point in space for every field. And every single one of them has this irreducible quantum jitter. And the vacuum is not still, it's trembling. And these tremors create something remarkable, virtual particles. And let me be very precise about what this means, because it's one of the most misunderstood concepts in all of physics. And The quantum fluctuations of the vacuum fields cause pairs of particles and antiparticles to spontaneously appear from nothing, an electron and a positron, a quark and an antiquark, a pair of photons. And they pop into existence, live for an incredibly brief time, and then annihilate each other, vanishing back into the vacuum. This happens constantly everywhere right now. And in the space between the atoms of your body, in the space between galaxies, and in every cubic centimeter of supposedly empty space, trillions upon trillions of these virtual particle pairs are appearing and disappearing every fraction of a second. Now, you might ask, are these virtual particles real? This is actually a subtle question, and physicists argue about it. You can't directly detect a single virtual particle in the way you detect a real particle. They exist below the threshold of direct observation, and they violate conservation of energy, but only for such a short time that the uncertainty principle covers for them. The more energy the pair borrows, the shorter they exist. It's a pair with the mass energy of an electron-positron pair lives for about 10 to the negative 21 seconds. A pair with more mass lives even shorter. And they're like ghosts that appear and vanish before anyone can catch them. But here's the thing. Even though you can't see individual virtual particles, their collective effects are measurable, and precisely measurable. And those measurements confirm that the vacuum is exactly as strange as quantum mechanics says it is. The most famous measurement is the Lamb shift. And in 1947, Willis Lamb measured the energy levels of hydrogen atoms with extraordinary precision. Hence, he found that two energy levels that should have been identical according to the Dirac equation, which describes the electron relativistically, were actually slightly different. Hence, the 2s half state and the 2p half state had a tiny energy splitting that classical theory couldn't explain the explanation. Virtual particles, hence the electron in the hydrogen atom, is constantly interacting with the virtual particles popping in and out of existence around it. Hence, these interactions shift the electron's energy levels by a tiny amount. Hence, when you calculate this shift using quantum electrodynamics, QED, accounting for all the virtual particle interactions, you get a prediction that matches Lamb's measurement to 10 significant figures, and 10 decimal places of agreement between theory and experiment. This is one of the most precise predictions in all of science, and it only works if you include the effects of vacuum fluctuations. If you accept that empty space is not empty, there's another measurement even more dramatic, the Casimir effect. And in 1948, the Dutch physicist Hendrik Casimir made a prediction so strange that it took decades for experimentalists to confirm it. Take two metal plates, and perfectly flat, uncharged, electrically neutral, place them very close together in a vacuum, separated by just a few micrometers. According to classical physics, nothing should happen. And there's nothing between the plates, nothing pushing on them. They should just sit there. But Casimir predicted that the plates would be attracted to each other, and that they would feel a force pushing them together, a force coming from nothing, from empty space. How? Here's the explanation. And between the plates, only certain wavelengths of virtual photons can exist. The waves have to fit between the plates, like standing waves on a guitar string. But outside the plates, all wavelengths are possible. There are no constraints, so there are more vacuum fluctuations outside the plates than between them. And this imbalance creates a net pressure pushing the plates together. And in 1997, Steve Lamoureux at Yale measured this force directly. The plates were pushed together by nothing, by empty space. And by the quantum vacuum itself, the measured force matched Casimir's prediction to within about 5%. Later experiments improved this dramatically. The vacuum is not empty, it pushes, it pulls. And it has physical, measurable consequences. Now, I want to tell you something that should keep you up at night. Something that is perhaps the greatest unsolved problem in all of theoretical physics. Hence, the vacuum catastrophe, also known as the cosmological constant problem. Hence, we can calculate the total energy of the vacuum, the sum of all those zero-point fluctuations from all the quantum fields at all wavelengths. And when you do this calculation, and every physicist who teaches quantum field theory does this calculation, at some point you get a number, and that number is absurd. Hence, the energy density of the vacuum, according to our best calculations, is about 10 to the 113 joules per cubic meter. Let me put that in perspective. Hence, the entire observable universe contains roughly 10 to the 69 joules of energy. Hence, and the vacuum, according to quantum field theory, contains more energy per cubic centimeter than the observable universe contains in total. This is obviously wrong. Hence, if the vacuum had that much energy, it would curve space-time so violently that the universe would be a tiny ball, or it would expand so fast that no atoms, no stars, no galaxies could ever form. Hence, the universe as we know it wouldn't exist, but it does exist, we're here, so something is desperately wrong with our calculation, but what we know vacuum fluctuations are real. Hence, the Lamb shift proves it, the Casimir effect proves it, the vacuum is not empty, it has energy, hence, but the amount of energy doesn't match what we predict by roughly 120 orders of magnitude. This is sometimes called the worst prediction in the history of physics. Hence, 120 orders of magnitude, that's not being off by a factor of 2 or 10 or a million, that's being wrong by a number with 120 zeros. And here's what makes this problem so profound. Hence, it's not that we don't have a theory of vacuum energy, we do quantum field theory, and that theory works beautifully for everything else. Hence, the Lamb shift, the Casimir effect, the magnetic moment of the electron, particle physics, all of it predicted with extraordinary precision. Hence, but when we apply the same theory to calculate the total vacuum energy, we get nonsense. The theory that works perfectly at small scales gives us garbage at cosmological scales. And something fundamental is missing from our understanding. Something about the vacuum, about empty space itself that we don't grasp. Now, Einstein enters the story. And in 1917, Einstein added a term to his equations of general relativity called the cosmological constant. Hence, he put it in to make the universe static, because at the time, everyone believed the universe wasn't expanding. Hence, when Hubble discovered the expansion of the universe in 1929, Einstein removed it, calling it his greatest blunder. But in 1998, two teams of astronomers made a shocking discovery. Hence, the expansion of the universe is accelerating, not slowing down due to gravity as everyone expected, but speeding up. Something is pushing the universe apart, making it expand faster and faster. Hence, and the simplest explanation is Einstein's cosmological constant, a tiny amount of energy permeating all of space, a constant energy density of the vacuum, pushing everything apart. Hence, the observed value of this vacuum energy is incredibly small, about 10 to the negative 9 joules per cubic meter. And compare that to what quantum field theory predicts, 10 to the 113 joules per cubic meter. The ratio between prediction and observation is 10 to the 122. And so the vacuum does have energy. The accelerating expansion of the universe proves it. Dark energy, as it's called, makes up about 68% of the total energy content of the universe. And most of the universe is vacuum energy. Most of what exists is the energy of empty space. But why is it so small? And why is it not 0, which would be elegant, or 10 to the 113, which is what we calculate? Why is it this absurdly tiny but not 0 number? Nobody knows. Hence, I've spent a significant part of my career thinking about this problem. Hence, I helped develop the string theory landscape, the idea that there might be an astronomical number of possible vacuum states, maybe 10 to the 500 different configurations of extra dimensions in string theory, each with a different value of the cosmological constant. In this picture, we live in one particular vacuum out of an incomprehensibly vast landscape of possibilities. And the reason our vacuum energy is so small is observer selection. If it were much larger, galaxies couldn't form, stars couldn't burn, and we wouldn't be here to ask the question. And this is controversial. Not everyone agrees with it. Some physicists find it deeply unsatisfying because it doesn't really explain why the vacuum energy is what it is. And it just says that it has to be approximately this value for us to exist. But controversial or not, it tells us something important about the vacuum. And empty space is not just something physics can ignore. It's one of the deepest mysteries in all of science. Let me talk about something else the vacuum does that's genuinely terrifying: vacuum decay. And there's a possibility, and I want to be very careful about how I phrase this, because the physics is speculative, but based on real calculations, there's a possibility that the vacuum we live in is not the true vacuum, that it's not the lowest possible energy state. It might be what's called a metastable vacuum, a false vacuum, a valley that looks like the bottom but isn't. If this is the case, then somewhere, at some point, a quantum fluctuation could trigger a transition to the true vacuum. That's a tiny bubble of true vacuum could nucleate, and that bubble would expand at the speed of light, converting everything it touches into the new vacuum state. And in the new vacuum, the laws of physics would be different, the constants of nature would change, atoms might not hold together, chemistry wouldn't work, life would be impossible. Hence, the bubble would be a wall of destruction sweeping through the universe at light speed, and you would never see it coming. Hence, because it moves at the speed of light, you couldn't detect it before it reached you. One moment you exist. Hence, the next moment, the ground state of reality has changed, and everything you are, every atom, every molecule, every memory is reconfigured according to new physical laws. And now, before you panic, the probability of this happening is extraordinarily low. And if the vacuum is metastable, its lifetime is probably fantastically long, much longer than the current age of the universe. And we don't actually know that the vacuum is metastable. Hence, the answer depends on precise measurements of the Higgs boson mass and the top quark mass, and current measurements are right on the boundary between stable and metastable. We're not sure, but the very fact that this question is meaningful, that the vacuum state of the universe could in principle spontaneously change, tells you something extraordinary about empty space. It's not passive, it's not dead, it's not nothing, it's a physical system with a state that could change. The vacuum is as dynamic and potentially fragile as anything else in the universe. Hence, let me bring this back to the Higgs field, because the Higgs is perhaps the most dramatic example of how the vacuum shapes everything we experience. Hence, the Higgs field is unlike any other field in the standard model. In our vacuum, the Higgs field doesn't sit at zero. Hence, it has a non-zero value everywhere in space, about 246 gigaelectron volts. This non-zero vacuum value is what gives particles their mass. Hence, the electron, the quarks, the W and Z bosons, they all get their mass by interacting with the Higgs field that fills the vacuum. Without the Higgs vacuum value, all these particles would be massless. Hence, they'd zip around at the speed of light. There would be no atoms, no chemistry, no us. Think about what this means. Hence, your mass, the mass of every atom in your body is not some intrinsic property of matter. It comes from the vacuum, from empty space. Hence, from the non-zero value of a quantum field that permeates all of reality. You're heavy because the vacuum is structured in a particular way. Hence, if the Higgs vacuum value were different, if it were zero, you would have no mass. If it were larger, you would be heavier. Hence, your very substance, your weight, the fact that you don't fly off at the speed of light is a property of empty space, not a property of you. And the Higgs is just the most dramatic example. Hence, every quantum field contributes to the vacuum structure. The electromagnetic vacuum allows virtual photon pairs that affect how charged particles behave. Hence, the QCD vacuum, the vacuum of quantum chromodynamics that describes the strong nuclear force, is even more exotic. Hence, the QCD vacuum is filled with what are called gluon condensates and quark condensates, non-zero average values of field combinations that give the vacuum a rich internal structure. Hence, the proton gets most of its mass not from the quarks inside it, which are very light, but from the energy of the gluon field inside the proton. Hence, the strong force vacuum energy confined within the proton is what makes protons heavy. And since protons make up most of the mass of atoms, and atoms make up most of the mass of you, most of your mass comes from the quantum vacuum structure of the strong force. Hence, you are quite literally made of vacuum energy, not in some mystical sense, in a precise, calculable, experimentally verified physical sense. The vacuum is your origin. The vacuum is your substance. Hence, the vacuum is the reason anything has mass at all. Now, let me tell you about something even more subtle and beautiful. The quantum vacuum is not the same everywhere. Hence, or rather, it responds to its environment near a massive object. Where space-time is curved, the vacuum fluctuations change. Near a black hole, this effect becomes spectacular. Hence, in 1974, Stephen Hawking showed that the vacuum near a black hole's event horizon creates real particles. The idea is this: a virtual particle pair forms near the horizon. one particle falls in, hence the other escapes. But because space-time is so violently curved near the horizon, the escaping particle becomes real. It carries away energy from the black hole. The black hole slowly evaporates. This is Hawking radiation, and it comes directly from the quantum vacuum. The same effect happens in an accelerating reference frame. If you accelerate through the vacuum, you see particles. Hence, the vacuum that appears empty to a stationary observer appears filled with thermal radiation to an accelerating observer. This is called the Unruh effect. Hence, what one observer calls empty space, another observer calls a bath of particles. The vacuum is observer-dependent. What's empty depends on who's looking. Hence, this connects to something I've thought about deeply throughout my career: the relationship between quantum mechanics, gravity, and information. Hence, the vacuum sits at the nexus of these three pillars of physics. Hence, understanding the vacuum properly, understanding why it has the energy it has, why it gives particles mass, why it creates particles near horizons, might be the key to quantum gravity. Hence, to the theory of everything. Let me tell you what really disturbs me about all of this. We live in a universe where 68% of all energy is vacuum energy, dark energy, hence the energy of nothing. And we don't understand it. We don't understand why it has the value it does. We don't understand why it's not zero or astronomically large. Hence, we don't understand its fundamental nature. Is it truly constant, as a cosmological constant would be, or is it changing with time, as some quintessence models suggest? We don't know. And this vacuum energy is determining the fate of the universe. Because of dark energy, the expansion of the universe is accelerating. Hence, in the far future, this acceleration will push galaxies apart faster and faster. Eventually, distant galaxies will recede faster than light. They'll cross our cosmological horizon. Hence, we'll never see them again. The observable universe will shrink, stars will die, galaxies will go dark, and the universe will become, ironically, more and more empty, except it won't be truly empty. Hence, the quantum vacuum will still be there, still fluctuating, still buzzing with virtual particles, still carrying its enigmatic energy density. Hence, in the far, far future, trillions of years from now, the universe might be nothing but vacuum. No stars, no planets, no life, and just empty space expanding forever, filled with quantum fluctuations that nobody will ever observe. The vacuum will be all that remains, the nothing that is actually everything. And here's what I find most profound. Right now, as you listen to this, you're surrounded by this quantum vacuum. It's between your atoms, it's inside your atoms, it's giving you mass, and it's holding your molecules together. It's creating virtual particle pairs in the space inside your skull, inside your heart, inside your lung. And the space you think of as empty is the most active, the most energetic, the most fundamental thing in the universe, and you can't see any of it. We evolved to see the macro world, hence rocks, trees. Other people, we didn't evolve to see quantum fluctuations or virtual particles or the Higgs field. Our senses show us a simplified version of reality, a cartoon, a sketch. Hence, the real universe, the one described by quantum field theory, is incomparably richer, stranger, and more beautiful than anything our eyes can show us. Empty space is a lie. And it's the biggest lie our senses tell us, because what we call nothing is actually the foundation of everything. Could I be wrong about any of this? Hence, could the vacuum be simpler than quantum field theory suggests? I don't think so. The experimental evidence is overwhelming. Hence, the Lamb shift, the Casimir effect, the anomalous magnetic moment of the electron, Hawking radiation from black holes, if we could measure it directly, hence, all of these confirm that the vacuum is exactly as wild as I've described. What we don't understand is the big picture, why the vacuum energy is what it is, how the vacuum fits into quantum gravity. Hence, whether the vacuum is truly stable, these are open questions, and they might be the most important questions in physics. Hence, after 50 years of working on this, I've come to believe that the vacuum is not just a background stage on which physics plays out. The vacuum is the main character. Hence, it's the thing that determines what particles exist, what forces act, what structures can form. The vacuum chose the laws of physics in our universe. Hence, not literally chose, but the particular vacuum state we live in, with its particular Higgs field value, its particular cosmological constant, its particular pattern of symmetry breaking, determines everything Different vacuum states would give different particles, different forces, different chemistry, different possible life forms or no life forms at all. We are products of the vacuum. We exist because empty space has the structure it has. And if that structure were even slightly different, we wouldn't be here to wonder about it. And so the next time you look at the space around you and see nothing, remember what I've told you today, that nothing is a quantum field seething with activity, and that nothing is filled with virtual particles appearing and disappearing trillions of times per second, that nothing contains an energy density, we can't explain that, nothing gives you your mass, and that nothing determines the fate of the universe. Empty space is not empty, it never was, and the more we learn about it, the more we realize it might be the deepest mystery physics has ever faced. It's a mystery that connects quantum mechanics to gravity, the smallest scales to the largest, the beginning of the universe to its end, all of it encoded in the thing we carelessly call nothing. That's what physics tells me. And after 50 years of listening, I've learned that when physics speaks about the vacuum, about the nature of empty space, you should pay very close attention. Because what it says is far stranger, far more beautiful, and far more terrifying than anything you could have imagined. Thank you for listening. Look around you right now at all that empty space. And it's not empty, it never was, and understanding why might be the most important thing physics ever does.